This is my lab setup. I have a signal generator here, an oscilloscope, and a spectrum analyzer. And here's my Proteus AWT. Also on the lab bench, if I just pan the camera around, you will see I have a space grade ADC and a space grade DTA converter. Now this particular Proteus unit is a 2-channel AWT. And at the moment, I have one of the AWG channels outputting a sine wave to this space grade A to D. And then this space grade DTA converter generates an output which has been captured by one of the ADCs within the Proteus unit. This is a close-up view of the Proteus AWT. So this particular unit is a 2-channel unit. Here's both differential analog outputs from the internal DTA converters. Then we have 2 single-ended analog inputs which connect to the internal ADCs. And there are some additional connectors related to markers and triggers and GPIO. So this particular unit contains 2 16-bit 9 gigasample DTA converters, as well as 2 12-bit 9 gigahertz, 2.7 gigahertz ADCs. This is the Wave Design Studio software that comes with the Proteus AWT. And as you can see, I can very easily generate different wave shapes, from the standard ones to wideband noise, and it's very, it's a very intuitive piece of software. So, for example, here, if I want to increase the number of cycles, and then I download that to the instrument. So it's a very easy way to generate various types of outputs from the AWG. If I now connect the AWG's sine wave output to this space grade ADC, I can then measure and characterize in real time the dynamic performance of this space grade ADC, metrics such as signal to noise, SFDR, etc. As I mentioned in the article, the Proteus unit is an AWT and also contains an internal receiver comprising 2 12-bit 9 gigahertz, 2.7 gigasample per second ADCs. So on my bench here, I have a space grade ADC currently outputting a digital sine wave. I connected this to one of the AWT's receiver inputs. I've written a MATLAB script which acquires and then stores the digital samples of this analog signal in the Proteus's internal memory. My script displays the acquired time domain samples and performs an FFT to calculate signal to noise, SFDR, etc. Now I could quite easily have got the space grade DTA converter to output a noise power ratio wideband signal and then write a MATLAB script to calculate the noise depth, that is, to measure the intermodulation distortion from the digitized samples. Likewise, I could have got the space grade DTA converter to output a modulated carrier and then write a MATLAB script, or use the communications toolbox to display a constellation diagram and calculate bit error rate. If you so wish, you can also run a loopback test of the Proteus unit, connecting its internal DTA converter output to its internal ADC input. To summarize, I was looking for a single box solution for transponder testing, and I've discovered that the Proteus AWT allows AWG single tone, wideband noise power ratio, and modulated carrier generation for multi-channel payload receiver testing. The WDS software allows phase coherent stimuli to be created quickly and intuitively. Secondly, the AWT's wideband ADCs can measure the performance of payload transmitters. The data captured by the ADCs can be streamed to the controlling host PC for analyses or stored within the internal waveform memory. Finally, you can use the AWT for complete back-to-back payload testing. It's AWG to generate RF outputs, which can be input to a transponder, followed by the AWT's RF ADCs to characterize the performance of the processed output from the transponder transmitters.